right, everybody's favorite part of chemistry, the Lewis dot symbols. Okay, Lewis dot is a way for us to visualize what a atom is doing with its electrons. Okay, and how we're going to make bonds associated with this. The first thing we're going to talk about is what atoms look like in their Lewis dot representations. So, start with hydrogen. All right, how many electrons does hydrogen have? If you said one without looking at a book, good for you. You're right. It's one electron. All right, there you go. Go ahead and give yourself a pat in the back. All right, so I've got hydrogen here. It's got one electron. All right, it's the same if I go down the periodic table and go to lithium and go to potassium. Each one of these is going to have one dot associated with it. All right? And notice that even though potassium and left out sodium. Sorry, sodium. Put sodium on there too. It doesn't want to be left out. Each one of these, even though they don't have just one electron, lithium's got 3, potassium's got 11 total electrons, right? And you keep going that, or not 11, sodium's got 11, and then potassium has more than that. What you are going to end up with is lots of different dots. But in Lewis dot terminology, we're just putting one dot there. Okay? We're only concerned with the valence at this point. So Lewis dot symbols, what we're looking at are valence electrons. Okay? So each one of these has one dot. And what we do is we like to represent the dots on 4 different sides of the atom. So if I pretend I had a little box here around each one of these elements, there would be one dot for one side of the box. Okay? Now if I move on and I go to, say, beryllium, okay? Beryllium has how many valence electrons in it? It's got 2. That's right. So the way I represent it is I've got to have a symmetrical side to beryllium. Okay? So for beryllium, for Lewis dot nomenclature, I'm going to write the 2 dots on each side. Even though I know the 2 electrons are both in the s orbital, I'm going to write the 2 dots on each side, and I want them to be symmetrical. Okay? The 2 dots here, I can do 2 dots here. And I cannot do is put 2 dots, okay, on an atom to make them uneven. Okay, it doesn't work for Lewis dot structures. If I come over here to boron, carbon, oxygen, nitrogen. I'm just leaving elements out all over the place today. Nitrogen, oxygen, and fluorine. I'll even throw neon in here as well. I'm not going to draw the boxes in for these guys. Well, I'll have you recognize that there are boxes around each one. For boron, there's a dot for 3 electrons that are in the valence of boron. For carbon, 1 on each. Okay? Now with nitrogen, I've run out of sides, right? So 1, 2, 3, 4. I have to put 1 more electron in. So pick a side, any side, and pair it up. Remember that these orbitals can only have 2 electrons. So each side is kind of like an orbital, right? So I can only put 2 electrons on each side. For oxygen, I have to follow that same rule of symmetry. Okay? So I put the 2 dots on top, 2 dots on the bottom, or I could use the sides. Both of them will work, just as long as it's symmetric. Fluorine. Okay? We've got 7 electrons there. Neon has got that full octet. Okay? Now, for potassium, I drew potassium in for a reason, and that's because potassium starts our 3rd row. And after potassium comes calcium. And calcium has 2 electron dots. Okay? And then there's these 10 electrons that are in the middle. And now what I'm going to do is I'm going to jump up and I'm going to pick something fun like copper. Right? So here's copper. And copper's got 2 electrons in the s and 9 in the d orbital. There's 11 electrons total. So, let's look at copper with 11 electrons total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? Well, that looks kind of crowded. Not to mention the fact that I've got dots on either side of the element. Okay? Let me show you what happens when we try to do this Lewis dot approximation with, let's do platinum. Okay? Actually, let's do gold. It's in the same row as copper. Okay? So gold has 2 electrons for the S, 1, 2 for the S. Right? It's still got those 9 Ds. So 1, 2, 3. Let's just write it the same way as I did with copper up at top. Right? So there's gold, but I've got the F electrons too that I have to account for. That's 14 electrons. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right? Now, that looks like a great little billboard to be putting on, Broadway, now showing gold, right? But it doesn't really tell us a lot as far as the bonding characteristics of gold. Trying to draw bonds there around the gold, it's going to be awfully messy. And the same thing with the copper. So for Lewis dot terminology, I don't use S and D nomenclature. Or, excuse me, not S and D, D and F nomenclature. I use S and P only. Right? So for copper, I would have the same electronic configuration as calcium. Right? 2 dots on either side. Because I have to ignore the D and the F. Otherwise, I'm going to get things that are messy. As a result, it's not great to use Lewis dot symbols when dealing with transition metals or elements that are lanthanides or actinides. Those are the F block elements. Okay? So these aren't great. So we tend to stick only with those elements that are in the S and the P. Okay? So let's see. So if I come out here and I go to the third row for this is arsenic and selenium. The arsenic and selenium. Did I pick the right row? Nope. I'm off by 1. That's right. It's germanium, gallium, selenium, and arsenic and selenium. Okay? If I look at this particular row, what are my electron dots going to be? Even though gallium has a lot of electrons in its outer shell, we only represent the S and the P. So gallium's electron dot structure is going to look exactly like that of boron. Germanium, like that of carbons. Arsenic is going to look a lot like nitrogen. And selenium looks a lot like oxygen. And if I throw in bromine here, what would you guess? What's it going to look like? You said fluorine. Congratulations, you recognize the pattern in the periodic table. Okay? So there we go. Those are electron dots, or Lewis dot symbols for each one of these elements. Okay? It should be noted that I've paired a lot of these things up. And when I do that, I get something that's called a lone pair. So for nitrogen here and arsenic, each one of these has a lone pair of electrons. These actually become very important later in the future. Okay? I've got more lone pairs here with selenium. There's 2 lone pairs in oxygen and selenium, 3 lone pairs in bromine, and 3 lone pairs in fluorine. Okay? The lone pairs have a great deal of importance for each one of these. Okay? All right. Now, when we have simple ionic bonds, this is actually a pretty easy representation. All right? So for ionic bonding, if I take something simple like lithium and stick it next to something like fluorine, lithium has 1 electron, and the fluorine has 7. Now, for the fluorine to get a full set of electrons, what it's going to want to do is it's going to want to pull the electron, sorry about that. It's going to want to pull the electron away from the lithium. Okay? That phone is blowing up. Of course, right in the middle of a video this happens. Now, the fluorine and the lithium, the fluorine wants to get that electron, and in doing so, gets that full octet. The lithium, on the other hand, wants to lose an electron, so it gets to that 1s2, that full first shell. All right? So what ends up happening is we get more of a transfer of an electron over to the fluorine. Okay? So the transfer happens, and what we end up with is a lithium with a positive charge and a fluorine with a negative charge. The fluorine is represented with all of its electrons here, okay, and the lithium is not represented with any electrons, even though it's got those 2 electrons in the inner shell. We represent this as a 0 valence, okay, rather than a 2 valence to avoid confusion. How do you lose an electron and go to 2? It would be kind of confusing. So instead, we just lose the electron and show this as an empty outer valence, which technically it is. All right. So what about if I had oxygen and I was sticking 2 sodiums on it? All right, so here's oxygen. Right, when I put 2 sodiums on that thing, what's going to happen? Well, each one of the sodiums is going to lose its electron to the oxygen. All right, and in doing so, what I end up with is an oxygen with a full octet, and what's going to be the charge if it gains 2 more electrons? That's right, -2. Good. That's a -2, and I can put 2 sodiums on either side. Okay? Each one of these has a +1 charge. I like circling the charges because if I circle the charges, it doesn't let me get confused with something that might be an electron or might be something else or a bond that's floating around out there. So I like to circle charges. If I'm going to write these 2 things properly in a representation of a compound, what I'm going to do is I'm going to write lithium fluoride. The metal always precedes the non-metal. Okay? And in this case, I've got sodium and an oxygen. And how many sodiums do I have? I've got 2. So I've got to represent the 2 there because there's 2 of those for every oxygen in the compound. So I've got to put the 2 down here. Don't put the 2 in front, because if I put the 2 in front like I do right now with this lithium, that 2 means that I've got 2 lithium fluoride compounds. This means I've got a compound that has 2 sodiums and an oxygen in it. If I put a 2 in front of this, that would mean I've got 4 sodiums and 2 oxygens. Okay, so if I'm representing a bound metal to a non-metal, or bound covalent structure, okay, I've got to make sure that I put a subscript or a coefficient next to each one of those atoms. Okay?